Hello, good afternoon everyone. I am Tohida Rehman from Jadavpur University, Kolkata, India. I am here to present our paper on behalf of all our co-authors, and I want to express my sincere gratitude to all my co-authors. The title of our paper is Named Entity Recognition Based Automatic Generation of Research Highlights. These are the main contents of our paper. Firstly, I will discuss the overview of our paper. Then I will discuss the dataset details and the data processing part. In the section of methodology part, I will explain the methods we used. In the evaluation result part, I will show you our model results, then comparison with some previous works, manual evaluation details, and some sample model generated summary also. Then I will highlight the conclusion and some future works. At the end, we have added some references. An abstract provides a high-level view of any research paper. Nowadays, abstracts have been enhanced with research highlight that summarize the main findings of the paper. That means research highlights a bulleted list of the main contributions. They are potentially easier to read than abstract, especially on mobile devices. In this paper, we aim to automatically generate research highlights using different sections of a research paper, such as we used input as abstract only, a combination of abstract and the conclusion, and the combinations of introduction and conclusion of the paper. We have used deep learning based models, a pointer generator network and pointer generator network with coverage mechanism, and augmented each of the above two models with named entity recognitions. We investigated whether the use of named entity recognition on the input improves the quality of the generated highlights. Practical implications of this paper is that proposed method can be used to produce highlights for research paper that with missing highlights. To the best of our knowledge, this work is the first attempt to use a near-in pointer generator with coverage mechanism to generate research highlights. We use the dataset published by COLING et al., which contains the URLs of 10,147 computer science publications from Science Direct. In our experimental setup, every example in this dataset is organized as follows: abstract, author written research highlight, introduction, and conclusion. We use 8,116 example for training, 1,017 example for validation, 1,014 example for testing. In data processing, we have removed digits, punctuation, special characters from the documents and lowercase the entire corpus. The retokenizer merge method of space is used to tokenize and merge several tokens into one single token based on the named entities in the document. See an example. Instead of individual tokens of artificial, neural, and network, we pass all the three tokens together as a single token artificial neural network that is referenced as vocab index 17. We organize the dataset as abstract is the input, then author-written research highlights is the output. Next, abstract and conclusion is the input, author-written research highlight is the output. Next, introduction and conclusion is the input and author-written research highlight is the output. Here, plus symbol denote the text concatenation. In this dataset, the average abstract length is 186 tokens, while the average author-written highlights length is 52 tokens only. When you consider abstract and conclusion, the average length was 643 tokens. When you consider introduction and conclusion, the average length was 1234 tokens only. We perform experiments with four variants: pointer generator model with coverage mechanism, NER based pointer generator model, NER based pointer generator model with coverage mechanism. We use pointer generator network as our baseline model. In all models, we consider maximum input tokens to 400 when the abstract is input, and for all other cases 1500 is the maximum input tokens. In all cases, the generated research highlights have a maximum token count of 100 only. In this slide, I will explain in details our model. In pointer generator model, it first tokenizes a document using Stanford Code NLP tokenizer and convert the tokens to word embeddings, and word embeddings are trained with the model. Our model consists of an NER-based tokenizer layer and pointer generator network. The NER-based tokenizer layer converts the words in the input document to a sequence of tokens, that preserving the entity name as a single token. We do not use pre-trained word embeddings. In our model, token embeddings are learned from scratch during training. Here, the main role of NER is that instead of directly feeding the normal tokens of the input document into the encoder, we are passing the NER-based tokens. This table shows the F1 score for Rogue 1, Rogue 2, Rogue L, Meteor, and BART score matrix for various input from the test dataset. You can see here among the four models, NER-based pointer generator with coverage mechanism achieved the highest Rogue, Meteor, and BART score in all cases. This table compares the performance of our proposed approach with other competitive baseline in the literature on the CS PubSum dataset in terms of ROGEL F1 score. A supervised machine learning approach is proposed by Collins et al. To identify relevant highlights from the full text of a paper using a binary classifier. Instead of a simple binary classification of sentences, highlights or not, Cagliario and Lagporta used a multivariate regression method to select the top K most relevant sentences as research highlights. Rehman et al. Used a pointer generator model with coverage mechanism with globe word embeddings to generate research highlight from abstract. It is showing that our designed architecture, linear-based pointer generator model with coverage mechanism is able to achieve the significant performance improvement compared to the state of the art. For manual evaluation, we recruited 16 human annotators to independently rate a given summary on a scale of 1 to 5 for adequacy and fluency separately. We performed manual evaluation for our best performing model only. NER plus PGM plus coverage mechanism. Model gives the best result. That's why we selected a set of 25 papers and their author written highlights and their highlights from the model M when the input is abstract only. Each summary was rated independently by two raters. Each rater was given the full text of a paper and either the author-written research highlights or machine-generated highlights of the paper, but not told which one. One fluency, the average score for A equal to 4.02, M equal to 3.3, while one adequacy, the average score for A was 3.82 and for M was 3.12. This shows the machine-generated highlights are only slightly worse than the human-written ones. We added three figures as a sample output generated by four models for various input types. In all case studies reported here, we highlighted example of factual errors by yellow color, repeating words by orange color, and correct name entities by green colors. In this case study, input is only abstract taken from this research paper, and model generated outputs are given in the next slide. You can see that without NER-based model generated many out of vocabulary words and factual errors, but NER-based model correctly generate the named entities in the output, that is Korean satellite and Korean satellite here. In this case study, input is taken as abstract and conclusion, that is taken from this research paper. Treating an entity as a single token in the input helps to learn better embeddings and results in more controlled generation of the output, thereby reducing semantically invalid word and phrases here. So you can see this model generated highlights are better than the other model. In this case study, input is concatenation of introduction and conclusion taken from this research paper. Our model reduced erroneously repeating words and more meaningful highlights are generated. You can see here. These are the conclusions of this research work. We applied 4 different deep neural models to generate research highlights from a research paper. The NER-based pointer generator model with coverage mechanism achieved the best performance in all cases. In future, we intend to investigate in detail why NER improves the generated highlights. We also aim to ensure that the generated highlights are correct in syntax and semantics. In this slide, we have added some references. Thanks for your listening. If you have any question, please contact us using this mail ID. Once again, thank you so much to the organizers of this workshop.